Learning Outcome 4.6. Calculate the response of applying a given input signal to a system described by a linear constant coefficient differential equation. We have our input signal x of t, which in an LTI system uses the impulse response to produce the output signal y of t, which is a convolution of x of t and h of t. We saw in Learning Outcome 4.5 that x of t can be transformed into x of j omega, and y of t equals convolution of x of t and h of t can be transformed into y of j omega equals x of j omega times h of j omega. We now want to look at the problem where we're given a linear constant coefficient differential equation, and instead of trying to find the impulse response, we want to find the response when that input signal is some function. For instance, 5e to the negative 3t u of t. What will y of t be in this case? You should know how to solve this in the time domain methods from the material you learned in your differential equations class, in which you reviewed in Chapter 2 when you used time domain methods to find the impulse response by way of the step response and ramp response. You could do it that way. And I bet that in your circuits class, in your differential equations class, they also showed you how to solve this with Laplace transforms. You could do that too. What I'm about to show you is very similar to that, but slightly different. So pay attention, and you need to do it this way when we're talking about finding solutions with Fourier transform methods. We saw in the previous learning outcome how we can take this differential equation, and from it we can find the frequency response h of j omega. And we know that y of j omega will be x of j omega times h of j omega. So for the example I showed, if x of t is 5e to the negative 3t u of t, what is x of j omega? Go look at table 4.2, pause the video, and come back when you have a good guess. Did you get 5 divided by j omega plus 3? We can now take that x of j omega and substitute it in, take our known h of j omega, substitute that in, and similar to the previous learning outcome, we're going to again use partial fractions to break this up in order to do the inverse transform. Okay, so what do we get? What value of j omega makes this term go to 0? Substitute that in to here, 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 and here. What value of j omega makes this term go to 0? Substitute that here, 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 and here. What value of j omega makes this term go to 0? Substitute that here, 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 and here. There we go. Partial fractions taken care of. Now we're ready to invert. Again, go back and look at table 4.2 of your text. Look for the 1 divided by j omega plus a. And you're going to see we're going to wind up with this combination. Again, the u of t's are very important, and your answer is incorrect without them. Okay, students have requested some more difficult examples in these videos. So what if instead I made the input x of t equals 5e to the negative 2t u of t? Looks pretty similar, but it's a little bit more difficult to solve. Our x of j omega, again, please go look at your table 4.2. We take that x of j omega, we substitute it in. We have our h of j omega, substitute that in. But now look that we have this j omega plus 2 term is repeated. Remember things you've learned in the past. With partial fractions, we now need to change the form of our partial fraction expansion. We have something constant over that j omega plus 2 term by itself, something over the j omega plus 2 squared, and something over the j omega plus 1. This part gets handled exactly like it did in the previous example. Okay, residuals still work for this. What value j omega makes this term go to 0? Substitute that here, here, and here. What value j omega makes this term go to 0? Substitute that here, 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 and here. Okay, we're 2/3 done. This a term's a bit trickier. So what we're going to do for that, again review the partial fractions video, is we're going to get a common denominator for these three terms, which will be the same common denominator we have in the previous line. So this a needs to be multiplied by another j omega plus 2 and a j omega plus 1. Our 20 has to be multiplied by just a j omega plus 1. And our negative 15 needs to be multiplied by j omega plus 2 squared. And here we have the numerator from the previous term. I've not written the denominators. They're the same on both sides, so we can ignore them. Okay, what's that a value going to be? Well, let's look at how many j omegas we have in each of these terms, because j omega is pretty rare in this example and easy to get to. In this example, in this term, we have a of them. Just multiply that out. In this term, we don't have any j omega squareds. In this term, we have negative 15 j omega squareds. And on the right-hand side, again, we have no j omegas squared. So in order for this to be a true statement, which it must be in order for this line to match this line, what does a need to be? It has to be 15. So now we know that a is 15. We finished our partial fractions expansion. Okay, now it's time to invert. Again, go to table 4.2. The first term and the last term are the same transform pair we used before. This middle one is the transform pair that follows it. And again, the U of t is important. Your answer is incorrect without it.